Maryam has received her PhD in 2018 from the University of Iowa with Dr. Greg Carmichael. And in her PhD research, she really focused on characterizing the chemical transport model errors using data from comprehensive field experiments. Most of you know her from her visits in AECOM in both 2017 and 2018, and she worked mostly with Frank and myself there and many of others in AECOM and NCAR on analyzing the FRAPPE field campaign data and assessing the impact of WRF-Chem parameterization on the prediction of ethane concentrations for oil and gas sources. Maryam's interests, and I would also say expertise, are really in the field of data analysis and assimilation and atmospheric chemistry modeling. And today, I believe she is bringing us up to Lake Michigan and telling us something about the LMOS campaign. So Maryam, the stage is all yours, and thanks a lot for agreeing to give a seminar.
Thanks, Gabby, for the introduction, and I'm very excited to give this presentation. So this work, the Lake Michigan Ozone Study, and our work started in spring of 2017 with the LMOS campaign. So I've been working on this in the last year of my PhD, and also after graduation, I continued working on this whenever I get a free time or whenever I miss WRF-Chem or doing chemistry stuff. So first of all, I want to thank all my co-authors from University of Iowa and also from other universities and agencies, all the collaborators on LMOS team. So this work wouldn't have been possible without their help and guidance. So this is the outline of my talks. I will start by giving a short introduction and motivation behind the study. So I will specifically try to explain the challenges of air quality modeling in coastal regions such as Lake Michigan region. And then next, I will talk about the Lake Michigan Ozone Study, LMOS, and the WRF simulation configurations that we tested in this work. Next, I will talk about WRF-Chem performance in capturing ozone and transport during the LMOS period. And also, towards the end, I will talk about the sensitivity study that we did to look at the impact of changes in NOx and VOC emissions on ozone production. Okay. So air quality modeling of coastal areas is a challenging topic. This is mainly because of the large influence of complex transport pattern and also errors in the emission inventory. They both can contribute to the ozone prediction performance largely. So these two factors can both impact the transport of ozone and its precursors, and also it can impact the ozone production efficiency in this area. So in the regions around Lake Michigan, we have seen high ozone concentration along the shore historically. So this have been observed in sites that are far from emission sources in all different states around Lake Michigan, and we have different regions in this area that are designated non-attainment for 2015 ozone standards. So another important point is that models usually cannot capture the high ozone event accurately in this kind of setup in coastal areas. So for example, here I'm showing an example of 3 different model prediction of surface ozone concentration on June 2nd of 2017. So we have the UIOA model using WRF-Chem, the Canadian model, and the US EPA model. So you can see, looking at the ozone concentration over the lake, you can see that each of these models predicted different values and different structure of ozone on this day. So really the main goal of this study, the LMOS field campaign, and also other campaigns such as Listos and Outlet is to look into the air quality problems in coastal regions and try to better understand the process of transportation and also ozone production in this area. Okay, so I'm going to talk a little about the land and lake breeze and also transport of different pollutants in Lake Michigan. So in summer, because there's a sharp gradient, temperature gradient between lake and land, we usually have the morning land breeze that transport the pollutant from land to the lake, and also in the afternoon we have lake breeze that will bring the air over the lake back to the land. So this here I'm showing kind of back trajectory analysis, or we can say that looking at the trajectory of different air parcels arriving at this point on the day that we had a strong lake breeze event using our WRF-Chem outputs. So we can see that how the pollutions from Chicago got transferred over the lake with land breeze and then transferred back to the land in the afternoon with the lake breeze. And similarly, we saw this same kind of circulation in the northern part as well. So on a normal day that we don't have the lake breeze, usually the air parcels that arrive at these two sites come from the west, and they don't necessarily pass highly polluted areas such as Chicago. So another point is that usually during the lake breeze, after this recirculation occurs, we see sharp gradient of ozone along the shore. So here I'm showing observation from a mobile lab, a GMAP. So this the car drove here along the shore and measured ozone on June 12, which was another lake breeze day. So we can see that the extent of the lake breeze and how much it got into the land by looking at the differences in ozone concentration, having a very high concentration of ozone along the shore, and then as we got few kilometers into the land, we don't see this high concentrations of ozone. So this is a clear indication of afternoon lake breeze that is bringing the polluted air over the lake back to the land. And then, so here I'm showing another day, June 9th. This is basically looking at MODIS satellite images, looking at clouds. And this is another way to look into lake breeze and then the extent of that. So on this day, we can see that we had a much stronger lake breeze that got like more than 150 kilometers inland. So the point here is that we can have different, the lake breeze basically can vary in different days. It can be strong on some days like June 9. It can have a clear recirculation of bringing pollution from Chicago back to the land, and it can also be like June 12, which has a very narrow kind of lake breeze event. So we can see that the point is that it varies every day here. Okay, so the Lake Michigan Ozone study happened in May and June of 2017. And as I mentioned, the main goal was to better understand ozone formation and transportation around Lake Michigan region. So we had different measurements and tools deployed for this field campaign. So we had two aircrafts, one NASA Geotasso, which was NASA aircraft which was equipped with Geotasso, measuring column NO2 and also air HARP to look at cloud and aerosols, and then scientific aviation that did spirals in different locations over the water, over the lake, and also over the land. So the scientific aviation aircraft, the Mooney aircraft, measured a few chemicals like ozone, NO2, methane, CO2, and some MET variables. So we had two main ground sites, Zion, which is north of Chicago, and it's on the border of Illinois and Wisconsin, and Sheboygan super sites. And then here I listed all the instruments that we had on these two super sites. And I'm gonna kind of show results or model outputs of these two sites in this presentation. So for the LMOS field campaign, University of Iowa was doing forecast, air quality forecasting with high, kind of 4 kilometers high resolution. And then after that, we continued testing different model configurations for our kind of post-campaign analysis. So here I'm showing our 4 kilometers domain. We had a single domain, and this is just a zoomed in kind of view showing the scientific aviation spiral locations and also Chicago, Zion, and Sheboygan sites. So here I listed the main configurations that we used. In the first table is what we used in our forecast and later in our post-campaign analysis. And in the bottom, I'm showing the configurations that we tested, basically. So we had 53 vertical levels, and we used MYN and 3 PBL scheme. So we used online Megan model for biogenic emissions, and for our chemistry initial and boundary condition, we used ECMWF-Chem's output. So in most of our, in almost all of our simulations, we had turned lightning off, but we also ran one simulation with lightning on. But on the days that I'm going to talk today, we didn't see a large contribution of lightning knocks to the knocks in the model. So it's okay that we turned it off on these days. So, and then for gas phase chemistry, I'm going to show results from WRF-Chem chemistry that we used, but then we also tested Mozart as well. And then we used Mozart for our emission sensitivity runs. And then land surface model for our forecast, we used 5-layer thermal diffusion option because it was a cheaper option. But then we switched to NOAA, and then we saw better performance with that. Again, for our forecast, we used the GFS-FNL 1 degree for meteorological initial and boundary condition. But then for our post-analysis, we switched into using her model outputs with 3 kilometers resolution, and we saw improvement when we used that. For anthropogenic emission, we use NEI 11 version 2 in our kind of first set of analysis. And then we reduced NOx by 28% to kind of accommodate the reduction in NOx from 2011 to 2017 based on EPA recommendation. We also tested photolysis option, FastJ, and TUV. So the options in green, I'm going to talk about the performance of the model using these green options. And then after that, I'm going to show how changing these options impacted the model performance. So let's first look at ozone, because that's what we are interested in. So here I'm showing time series of model in green line and also observation in black dots of ozone at Zion site. So I also put this figure here as a reference so you can see the location of the sites. And also similar plot for Chicago. So we can see that looking at these plots, we can see that model captured the trends, and there are no variability of ozone concentration well during the field campaign. But it consistently missed the high ozone concentration during the day, especially at Zion site. So the gray shaded areas are the days that we defined as high ozone event days in our study. So for example, June 2nd, you can see that we observed ozone up to 90, but the model didn't really reach that, and then it didn't predict values higher than 70 or lower. And then here I'm showing the average daytime ozone in the background, this is the surface ozone in the model, and circles show biases in air station. So this is average daytime. And we can see that we are seeing negative biases along the shore of Lake Michigan, which is kind of consistent with the results that we saw in the time series. So we really wanted to know why we are not capturing this maximum ozone concentration. So first we started looking at the meteorology to see if we are capturing the meteorology correctly in our simulation. So here I'm showing temperature and dew point temperature time series, comparing model and observation. So you can see that we successfully captured temperature and also dew point temperature at Zion site. And looking at, again, the looking at the domain and looking at biases across the domain, the model performance is pretty good in capturing temperature and dew points. And here I just included some of the statistics that we compared with some references. And in all of them, temperature, dew point temperature, and wind speed, we did a pretty good job in our model. So another kind of comparison that we did was that we compared WRF-Chem cloud fields with GOES 16 satellite measurements. And then, so we can see that WRF-Chem had good skill for mean and median of cloud optical depth, but we have some we kind of underpredicted number and fraction of low and high level clouds, and also overpredicted multi-deep clouds. But these results have been also seen in other WRF-Chem simulations. So it's just, I think it's just one of the known issues of WRF-Chem in capturing clouds. We also looked at the 2x2 contingency table. So this is based on the threshold for cloudiness. So basically looking at cloud optical thickness, anything with cloud optical thickness higher than 0.3 is counted as cloudy, and lower is clear. So we can see that WRF-Chem kind of predicted the cloudy and clear sky correctly 67% of the time, which is a very good and acceptable performance for WRF-Chem. So basically the point is that clouds were captured pretty well in our simulation as well. So in this slide, I'm kind of showing the sensitivity that we saw by changing the land surface model and the initial and boundary condition in our simulation. So you can see the green line is the results that I've already shown. So this uses HRRR for model outputs and uses NOAA land surface model. So after, if we switch these options and use FNL, or if we use a simple 5-layer thermal diffusion, we saw underestimation in temperature and overestimation in dew point temperature. So we got a pretty strong signal to these on these two variables after changing these options, which shows that it's important to pay attention to these configurations, especially if you are trying to simulate a region similar to the Midwest. And then here I'm showing kind of the spatial differences between the forecast, which is using FNL initial boundary condition with 5-layer thermal diffusion. So we can see that we saw a big kind of signal to temperature and dew point temperature after changing these options across the domain. And this is not just limited to the coastal site. So the point here is that using HRRR high resolution model output for an initial boundary condition really helped our simulation. And I highly recommend that if you are running simulations, I think it's available after 2015. So if you're using simulations after this time, looking at CONUS, you can use HRRR NOAA. You can use HRRR model outputs, and it can improve your model performance. Okay, So how changing these options and improving the kind of meteorology impacted ozone concentration in our simulation? So we see not small, like we see some changes in ozone concentration when we are looking at time series of Zion and Chicago. For example, we see higher maximum concentrations on some days when in our best kind of model performance compared to the forecast one. And then looking at the statistic, we can see that it's helped the model performance in capturing ozone. But we are still missing the maximum ozone concentration, and we need to know why this is happening and why these underestimations of ozone are in the model. So another very important factor that impacted our ozone forecast was changing the photolysis option. So in the simulations that I showed you, we were using FastJ with WRF-Chem chemistry. And then we ran another simulation using Mozart chemistry with TUV in WRF-Chem version 4. And we saw a very strong signal on high ozone events, especially on June 2nd. So you can see that the red line, which is our WRF-Chem using FastJ photolysis option, under predicted ozone on June 2nd, but then after switching to Mozart TUV, we kind of increased ozone by up to 20 ppb on this day. So this is a kind of a big improvement. But then the interesting point is that we are not seeing this changes on every day. It's just some day that we see that FastJ and Mozart are FastJ and TUV are kind of performing differently. And looking at the average, comparing these two simulations, we can see that we saw a strong signal, strong change in surface ozone concentration after switching to Mozart TUV, and then we are seeing higher ozone over the lake in this simulation compared to like WRF-Chem FastJ. Okay, so I'm gonna now focus more on June 2nd day because it's an interesting day, and we had a very like clear lake breeze on this day, and we are seeing the largest bias on June 2nd. So we're gonna focus more on this day for the rest of this talk. So here I'm showing, like trying to show the changes in wind field that happened on June 2nd with these plots. So it's a little bit busy, so I will walk you through this. So the first line is showing NOx surface concentration, and then the second line is showing ozone surface concentration. And then these are model outputs from 2 a.m. on June 2nd, and then I plotted these every 3 hours. And then I put this a back trajectory run, just show you like how the air circulation was on June 2nd. So here we see NOx over Chicago at 2 a.m. and then how the wind pattern changes, and the winds are now blowing from the west. And these winds are bringing NOx and pollutant over the lake, basically. So at you can see that at in the afternoon we saw kind of a switch in the wind direction over the lake, and now now winds are blowing from the east as we go into the afternoon. And then we can see that the extent of the lake breeze here seeing very high values of NOx. And then similar kind of time for ozone that we see low ozone early in the morning and nighttime. So low values of ozone over the lake. And as we move the pollutions over the lake, we see that the ozone concentration is growing larger and larger. And then at 5 p.m. in the afternoon, we can see that how these high values of ozone concentration get transferred back to the shore. Okay. So on June 2nd, we looked at the wind performance in more details to see if we captured the lake breeze correctly or not. So this is observation from SODAR instrument at Zion. So here. So we have like basically measurements of wind direction and wind speed at higher altitudes. So we compared these measurements with our WRF-Chem output. So we can see that we had westerly winds coming, starting at 0 local time. And then during 9 a.m. In the morning, you can see that the wind direction switched from westerly to easterly, which is an indication of lake breeze at Zion. So WRF-Chem captured this shift in wind direction pretty well with only 1 hour delay, which is a pretty good performance. And in these two plots, I'm showing wind speed, sorry. So we can see that we have, we also see the change in wind speed, so lower wind speed during the lake breeze, which was captured in the model. We also looked at the cloud fields, looking at those satellite and compared it to WRF-Chem model at different hours. So we can look, focusing on south of the lake, we can see that we didn't have clouds at the south of the lake at this day. We have some clouds on the northern side, but this does not impact our ozone production much. And also, we are having lower clouds in our model, so this means more ozone production, which is not something that we have in our simulation. So basically the point is that in the area that we are interested in and the high ozone production is happening, we didn't have clouds on June 2nd. And then, so here I'm showing the observations along the shore on June 2nd, and you can see very high values of ozone concentration were observed on this day, but model did not capture these values. So to better understand what's going on, because basically we are capturing the winds pretty well, and then the meteorology too, and we captured the timing of the lake breeze correctly on June 2nd. So another thing that we looked into to see and try to constrain the model errors was using different emission inventories. So these are results from our very recent runs. So these are all preliminary results. So if you have any suggestion, recommendation, I would really appreciate that. So I'm going to walk you through these emission inventories that we used. So first one is NEI 11 that we used for all the simulation up to now with reduced NOx emission. So also we looked at the impact of volatile chemical product on ozone production. So we got NEI 14 with VCP or volatile chemical products and without VCP emission inventories. So these were provided to us by Brian McDonald and Stu McKean. And here I put some details about this emission inventory. So another simulation that we did was that we use NEI 2017. This is based on NEI 2016 with updated EGU emission. And this was provided to us by EPA for the LMOS period. And this is daily emission, basically. So we run WRF-Chem simulations using our best configuration for using these for emission inventory. So in the next couple of slides, I'm going to compare kind of these emission inventories. And then after that, I will show you how this impacted the predicted ozone concentration in the simulation. So here I'm looking at kind of total emission for non-methane VOC and NOx, looking at the LMOS domain. And this is kind of the same thing, but just focusing on Chicago to look at the kind of compare the urban versus kind of the whole domain that contains urban and rural. So here looking at non-methane VOC, we can see that NEI 14 with updated VCP emissions predicted included the highest VOC emissions. And then other than no VCP, NEI 17 had the lowest compared to 2011. Looking at NOx, we see that NEI 11 had the highest NOx, and then after that NEI 14, and then NEI 17 has the lowest NOx emission. So we see also almost a similar pattern in Chicago with bigger differences in non-methane VOC when comparing different inventories. And then here I just included a map to show the spatial distribution of non-methane VOC in our domain. So another kind of factor that was different in our different emission inventories was the kind of VOC speciation and the emission for each VOC species. So we can see that comparing these emissions, we can see that NEI 14 with VCP had the highest emission rate for most of the VOCs, but we can see in some of them that NEI 11 or even NEI 17 had higher emission rates. So this is the part that tools such as integration reaction rating, WRF-Chem, can really help us identify the key VOC in the simulation and identify the kind of key reactions that result in ozone production. So plots such as this that you can create using IRR tool and perm analysis package that shows the most significant VOCs looking at different regions or different trajectories can really help us. So this is something that we are working on right now. I was hoping that I could have some results for this, but these are still very preliminary and we need to look more into that. So back to comparing emission inventories, another very important factor that is different in our inventories is the diurnal cycle of different species, like diurnal cycle of emission rates can be different in different inventories. For example, here we are looking at, so this is 24-hour diurnal cycle of non-methane VOC in different emission inventory. So comparing NEI 11, the green line, with NEI 17, the red line. So you remember that we had in NEI 11, we had higher VOC emission compared to NEI 17. But then we can see that when we look at the diurnal cycle, we see that during the daytime, actually non-methane VOC emission in 2017 is higher than 11, but nighttime is the other way around. And this can really impact our ozone chemistry over the lake, especially with different timing of land and lake breeze. It really can change the kind of the ozone production regime over the lake, depending on these differences. And then looking at NOx, we see a really kind of the largest difference happened during the day, that we had really higher NOx emission rate in NEI 11 compared to the other three emission inventories. Okay, so how these differences in emission inventory impacted the ozone concentration. So here I'm showing surface ozone concentration, the differences between NEI 14 without VCP and with VCP. And this is averaged during the campaign period. So we can see that we know that we have lower VOC emission in NEI 14, and this resulted in lower ozone over the lake. this is basically, we saw a large, again, saw a large sensitivity of ozone to changes and changes in VOC emissions. So in NEI 14, we have higher VOC and we saw higher ozone over the lake. And then next, comparing again, comparing NEI 11 with NEI 14 with VCP. So we had a higher NOx emission in NEI 11 and lower VOC emission. So how this kind of translate to ozone was that it resulted in higher ozone concentration in NEI 11 in rural sites. So we see lots of red in rural, meaning that higher ozone concentration in NEI 11, and then lower ozone concentration in cities, which you can see with blue color. So basically, kind of you can say that in rural site, we are more NOx sensitive, and then in cities we are more VOC sensitive. And then, so this is also another interesting output is comparing NEI 17 with NEI 14 with VCP. So in NEI 17, we have lower NOx and lower VOC emissions. So this translated into higher ozone in cities, but much lower ozone over the lake. So this kind of gives us a sense of how mitigation policies of controlling NOx or VOC emissions can impact the ozone concentration. But again, these are preliminary results, and we need to look more into these. So these are time series comparing these different simulations at Zion, looking at ozone. So we saw a kind of a signal and more ozone concentration on June 2nd, as I showed you in our NEI 14 with VCP. And NEI 17 predicted the lowest ozone on June 2nd. So we see a similar signal on some of the other high ozone event days. But then on other days, the differences between these emission inventories are smaller. And that basically shows kind of the impact of lake breeze and having their circulation on these days. So basically you have these differences in ozone concentration over the lake, but you don't necessarily see them when you are looking at the observations along the shore. You only see these differences or this kind of underestimation in modeled ozone on the days that you have lake breeze and you see kind of the air over the lake coming into the land, so you can basically measure it. This kind of highlights the need for more measurements, especially over the lake, can help us constrain the ozone prediction there. And also this plot, I just want to point out, shows formaldehyde concentration at Sheboygan site. So this site is further from the emission sources. So again, you don't see a big sensitivity when changing the emissions to formaldehyde, basically because it's further down downwind. So we need more also. We also need more from formaldehyde measurements on other sites as well. So looking at the statistics again, we can see that we improved our ozone prediction in our NEI 14 with VCP compared to NEI 11, our base run, and also NEI 17 simulation. So this is kind of making a conclusion from this section of this talk. So the point is that even if the model captures the lake breeze correctly and the transport correctly, the perturbation in VOC and NOx emission can impact the modeled ozone concentration over the lake and along the shore. So here I'm showing ozone concentration at 6 p.m. on June 2nd. in different kind of simulation using different inventories. So NEI14 with VCP, NEI14 no VCP, 17, and NEI11 with reduced NOx. So you can see that the structure can be the structure of ozone can be different in looking at these different simulations. So this is kind of points out that even small errors in emission rates and in our emission inventory can impact the ozone concentration that we predict in the model greatly. And you can also, I want to also point out that you can see the extent of the lake breeze in these simulations as well by seeing high values of ozone concentration along the shore. And then here I'm showing our first simulation using WRF-Chem class J that we predicted the lowest ozone concentration, basically trying to point out that other factors such as photolysis option can also play a very important role in predicting ozone concentration. So you can see that not having the correct chemistry and over the lake, we can see that in the regions that we're seeing high ozone concentration in the observation, and also in some of our model simulation, we're having very low ozone concentrations instead. So instead of having high ozone, we're depleting ozone along the shore in this simulation. And then, so this is just looking at formaldehyde to NOx ratio, which is used to kind of assess VOC versus NOx sensitivity of an area. So here I'm showing NEI14, 17, and NEI11 at 1 p.m. and at 6 p.m. in the bottom row. So basically, I'm trying to point out here that the sensitivity to NOx and VOC, which is assessed kind of approximated by looking at FNR, can vary between different simulation using different emission inventory. For example, here, if this FNR value is lower than 1, it indicates VOC limited area. And if it's higher than 2, it's more like a NOx sensitive area. So looking at 6 p.m., we can see that we saw in our NEI14 and NEI17, we saw more of like a NOx sensitive regime over the Lake Michigan, and also in the south side, like some part of the Lake Michigan in the south. But then in the NEI11, we saw more like a VOC sensitive regime. So this is another kind of indication of how errors in emission inventories can translate to ozone production efficiency. And as I mentioned, tools like integration reaction rate in WRF-Chem or trajectory analysis using either flex part or WRF-Chem kind of tracking option can help us look more into ozone production efficiency and kind of analyze NOx versus VOC sensitivity in our region. So I'm just gonna stop here, leaving my summary and conclusion, and I'll take questions. Thank you.
Thank you very much, Maryam. That was excellent.
Thank you.
So Carl just alerted us that we are still being recorded if you have joined the meeting later and haven't heard the early announcement. So yeah, so let's open the floor for questions. And simply unmute yourself and start talking, and we'll organize it that way. So I can't see everybody. So because if nobody else has questions, I would like to just start the discussion, because in some ways the differences among the different emission inventories are pretty large. So given that the impact on ozone was actually surprisingly small, And the difference between using the two different chemical schemes seem to be much larger than that. So it's, and I mean, I've seen that before where, you know, it seems like to change a lot in the emissions, but the ozone concentrations don't change quite that much.
Yeah, compared to photolysis option, these changes are much smaller, you're right, but we are still seeing differences in ozone concentration.
Right.
But there's also changes in kind of the VOC versus NOx sensitive regime is something that we need to look more into, that is causing like a big difference. That is kind of, that varies between different emission inventories. Yeah.
Yeah. And that's maybe also something I just remember from Frappé, that specifically looking at formaldehyde versus NO2 ratios, where you define these different regimes can vary significantly on region. Like in the Colorado Front Range, for example, we have a very, very large transition regime, a regime where you just cannot clearly say if your system is more sensitive to ozone or NOx. Versus in other regions like Houston, they saw a much clearer distinction. So I think that might be something else that needs to be considered when looking at the formaldehyde to NO2 ratio.
Yes.
I've got a question.
Sure, Carl,
Yes.
go ahead.
I've seen at least one case this August where there's high ozone from WRF-Chem over the lake. Is that realistic in terms of measurements? Just
So I know that this year very high values of ozone were measured along the shore. So probably that's right. I don't know. I need to look more into that. So, but given the fact that we were usually underestimating ozone over the lake in our simulations, so we need to look and see what setting and configuration and emission inventory was used in that WRF-Chem simulation.
Yeah, I can jump in, but yes, we do observe high ozone over the lake during these periods. During LMOS, we did have some ship transects across the lake, and that measured elevated ozone. But as Maryam said, more observations over the southern part of the lake would really be good. And we did have some, which she didn't talk about. We had some aircraft observations that we compared with as well, and it showed that what was happened in the very shallow layers above the lake. So challenging.
Yeah, there was also a field campaign that happened, I don't know, many years ago. That was led by LATCO, and they have ship measurements over the lake, and they measured very high ozone and NOx concentrations over the lake. So it is something that is expected.
I have a question. I guess the question is also how well is WRF-Chem doing with deposition over the lake? I have no idea. That's maybe a question also for the entire audience. That has, we don't even know exactly how well it is doing over land. I don't know how well it is doing over ocean. Yeah. So, any other comments? Question.
Yeah, I have a question. This is Audrey Codell, working at NOAA. Very nice work, Maryam.
Thank you.
I work on tropospheric ozone background, and I was just curious because I couldn't remember the biases between the model and the observations when you showed the differences between the model results regarding the different inventories. I guess it's related to what Gabby was saying. I was just wondering if the range of the difference is actually explaining the difference between observations in the model.
So we have, okay. So here, I guess I'm trying to, like, one point that we need to consider is that we see the largest sensitivity over the lake. So when we are changing VOC emissions, we see a large signal for in ozone over the lake, but then that doesn't always translate into what we see along the shore. You know what I'm saying? So is that we don't see these impacts such as the one that we see on June 2nd on every day, because we didn't really transport that air mass that is sensitive to emissions back to the shores and to the sites.
Yeah.
So if you
okay.
want to really look into that, we need to kind of have measurements in the south side of the lake over the water, and then compare that. Probably we will see larger sensitivity, especially to VOC emissions over there.
Mm-hmm. Yeah, exactly. I was thinking about the shore. So yeah, okay, I understand. Thank you very much.
Hi, Miriam. This is a nice talk. Thank you. I just have a general question for WRF-Chem modeling, which is, isn't it generally more important to get the meteorology right anyway when you're comparing to measurements?
Well, that's I think that's basically the whole point here, that even if we get the meteorology right, which is what was happened, especially on June 2nd, and also in general, we did a very good job, but we failed to capture the high ozone concentration. So the point here is that there are many factors that can contribute into ozone prediction. Meteorology is one of the important ones, one of the most important ones. But getting the meteorology right doesn't necessarily translate to capturing maximum ozone concentration correctly.
Thanks.
Yeah. Do we have any more questions? And I definitely second that what Miriam said, that it seems like getting the meteorology right is a prerequisite. But even then, we have a lot of other challenges to overcome before anything looks right. And of course, this is also a very challenging, a region that you're looking at with the land sea breeze. And specifically, I assume, have you had any chance on looking at boundary layer performance, specifically in the coastal areas?
So you're talking about chemical boundary layer, or?
Well, in general, it's just the mixing layer, the boundary layer. If you have any
okay.
boundary layer, if you have any ceilometer data, maybe, or
yes, I didn't include that here. So we have ceilometer data at Sheboygan site. So I have details. We have details on that in the JGR paper. So we captured the kind of the mixing ratio heights when we compared the ceilometer data pretty well in Sheboygan site.
But do you get the morning rise and the evening in the boundary layer? Because this often, I know that often, like what I see in WRF-Chem, often we get the daytime boundary layer right, but we get the rise and the decline of the boundary layer wrong. And that means also we already have errors in the buildup of the chemistry. Especially the problem is early morning you have the rush hour. If now my boundary layer in the model is off in timing or something, or it doesn't rise sharply enough, I mix my emissions in the morning already very differently than really happens in the reality. And you start already your entire chemistry off the wrong foot.
Yeah, that's a really good point. There's also the difference between the PBL height over land and over the lake. So when we are transferring all these pollutions over the lake, like we kind of traps that over the water with lower boundary. And then like during the lake breeze, I didn't include the PBL height plot, but you can see like the same way that we saw a gradient in ozone concentration, we also see a gradient in PBL height. So with lake breeze bringing the air that's over the lake to the land, we see that like low PBL height on the shore with high ozone concentration. Mm-hmm. So capturing that is also pretty important too.
Yeah, just to follow up on that, I mean, these are all great questions. And we continue to look at that, but clearly getting the boundary layer evaluated over the lake is really important. And there we have some aircraft profile data, and I think it shows that our model boundary layer is a little bit too high over the lake, and so we haven't really looked at interventions on that. But I guess the other thing that's happening, of course, is that under the COVID period, you know, we do have observations occurring, and so that we're going to continue to use this modeling system to see if that'll tell us more about the NOx sensitivity and VOC, but certainly there's a strong NOx change. So, yeah.
Mm-hmm. Yeah, it's definitely in that regard, it's a good testing period. We wouldn't really have needed that experiment, but I guess now that we have it, we can as well use it.
This is Charlie Stanier. I'm just looking at Maryam's JGR paper, and for at least for June 2nd, we got the timing of the rise and collapse of the boundary layer correct at that Zion site, and we got the height at its peak correct. That's not true for every day. Mm-hmm. And then at the Sheboygan site, they have high vertical resolution thermal profile, and the lake breeze came in at like 50 meters thick, right, in the real world, and in the model it was quite a bit thicker when it came in. So getting these really like 20, 50 meter layers of cold pool over the lake is very difficult.
Thanks. Yeah, can definitely see that. Yeah. Do we have any final question before our time is over? Because if not, then I would like to thank Maryam a lot. It's really great work. I'm looking forward when you start using the IRR, and specifically, I'm still very taken by that large difference that you had between WRF-Chem and the Mozart chemistry on this one day. So learning more about the chemistry and what happened there will be really, really interesting, I think.
Yeah, thank you for having me.
Thanks very much, everybody. Ivan, are there any announcements to make or anything?
No, there is nothing. I guess we have another seminar next week. So look, we will send the flyer, I guess, tomorrow or this week.
Yes. So stay tuned, and thanks everybody, and enjoy the rest of the evening then.
Bye-bye.
Thank you. Bye.
Thank you. Great talk.
Hi, thanks. Great talk.
Thank you.